So for today, let's talk about this idea of a bipartite graph. So this is the definition of a bipartite graph, meaning that we can have two partite sets, x and y, so that every edge only incident to one vertex in x and one vertex in y. That's called a bipartite graph. And note that the graph K1 is considered a special bipartite graph. In this work example 3.1, we need to show that this is bipartite graph. Let me introduce you a special way of looking at that, that is through coloring. So if I color U with red, so X with red, then Z with red, then we can see that we already make it into two sets, where one set considers the vertices U, X, and Z, and another set consists of vertices W, V, and Y. So this is the work solution. It's very easy to determine whether the graph is bipartite. Surely, D and E is not bipartite because it considers a triangle and a pentagon. If we're going to color the vertices as black, white, it is not possible. So with this, then we can see that if it contains odd cycle, then it is not bipartite. Or equivalently, we say that if it's bipartite, it contains no odd cycle. And this is a very important criteria to determine whether a graph G is bipartite or not bipartite. And naturally, we are asked, if G contains no odd cycle, must G be bipartite? And the answer is yes. You do not give a proof, but this is the important result for this chapter 3. So let us look at result 1. Let G be bipartite graph with bipartition xy. Then the sum of degree in x and the sum of degree in y, they are all the same. And it is actually the number of edges in G. So let's say this is x, this is y. So we already know that the edge must incident one end in x and one end in y. It means that all the edges might come from x to y. All the edges in y will receive edges from x. It means that the number of edges come out from x will be equal to the number of edges come out from y. That's why we have this result. And it's exactly the number of edges in the graph G. And it's just like the idea of complete graph. We have this complete bipartite graph if each vertex in x is adjacent to each vertex in y. And we say that there's only one and only one up to isomorphism complete bipartite graph with a given bipartition xy. In this case, the symbol is KPQ. So let's say, for example, K23 will be something like this. K33 will be another graph which look like this. It's a famous challenge for you all, that is it possible for you to redraw the graph K33 on the plane such that there's no crossing among the edges. It can be done for K23. So for K23, we can draw it in this way. This is a 3 vertices and another 2, so we can draw the K23 in this manner without crossing. But you can try for K33, no matter how you draw it, it always have at least one crossing. Okay, next, we have exercise 3.1. Say that let G be a bipartite graph with bipartition xy. So that if G is regular, where K is at least 1, then the number of vertices in x equals the number of vertices in y. We need to recall the result. The sum of all vertices in x and the sum of all vertices in y, they are the same. Since G is K regular, then the degree of x is equal to K for every x in x. Also, the degree of y is K for every y in y. On the left hand side, it is K multiplied with the number of vertices in x, and on the right hand side is the k times the number of vertices in y. Here is very important condition that k is at least equals to 1, meaning that k is not equal to 0, then we can cancel the k, and that's right, the number of x equals to the number of y in this case. Now go to question 2. Construct all non-isomorphic graph of order 8 vertices, and size 10. So size 10 edges that are bipartite and contain a C8. Now, when it contains a C8, then we know that there must be two sets x and y, so that this happening. So let me color y as black. So from the partial result, we can redraw it as, then it's easier for our construction. So black, white, black, white, black, white. Now it's order 8 bipartite. Size 10 means that we need to put in another 2 edges. This extra 2 edges may incident to a particular vertex. So let's say this is the particular vertex, so it will join to this and another one. That's the only choice. So the next example, which is not isomorphic to it, the extra 2 vertices will incident to all different vertices. So meaning that if we join here, then I need to join like this. For example, I claim that these two are not isomorphic is because the subgraph induced by all degree 2 vertices, they are different. So one will be a union of 2 K2, and the other one is a union of K1 and a path. So they are 2 different graphs. So with this, these are the only 3 non-isomorphic graphs of order 8 and size 10 that are bipartite and contain a C8. So we'll move on this question 3. Show that there does not exist a bipartite graph with degree sequence many of 6, 5, and many of 3. So we prove by contradiction. Suppose not, let V belongs to Y such that degree of V is equals to 5. We know that the sum of all degree x in x equals to the degree of y in y. And since V belongs to Y, so we will have on the left hand side 5 plus the rest. For the rest of vertices is either of degree 3 or degree 6. So it means that the rest of the degree, when we sum it up, it is equals to a multiple of 3. Likewise, for the sum of degree in y, it will be a multiple of 3. And therefore, 5 will equal to 3L minus 3K, which means that 5 is a multiple of 3. That is a contradiction. And because of this, our assumption just now is not correct. And therefore, we conclude that there does not exist a bipartite graph with degree sequence as such. Question number 4. Let G be a bipartite graph with bipartition xy. Assume that the size and the order of G the same, and the degree of x is not more than 5 for each vertex x in x. We need to show that the number of vertices in y cannot be too many and is bounded by 4 times the number of vertices in x. The sum of vertices in x, the sum of the degree of vertices in y. And for this, it is equals to the number of edges in G, and in this case, it is given by the number of vertices in G. So the number of vertices in G is just simply x and y add up together. This is the information that we can have. So we need to use only the useful information. The sum of degree in x equals to the number of element in x and the number of element in y. So let's look at this again. A degree of x is less than or equal to 5 for every x in x. So the sum of this will be less than equals to the sum of 5 for all x in x. And we know from the above, this is equal to number of elements in X plus number of elements in Y. On the right hand side, this is equal to 5 times the element in X. And therefore, we have the result, number of elements in Y less than or equal to 5 of element in X minus 1 of element in X, that is 4 of element in X. Okay, let's move on. Question number 5. What is the largest cycle in KPQ, where P is in between 2 and Q? So let's say there are P vertices here and Q vertices here. So the largest cycle that we have, it must one from P and one from Q, one from P, one from Q, one from P, one from Q, and so on and so forth. And we see that once you use up all the vertices in P, then we have to join back to the initial vertex in P. So in that case, the largest cycle will be equal to 2P. And next, what can say about the complement of KPQ? For all these P and Q, the complement of KPQ, this will become a KP, and this will become of a KQ. So the complement of this will be a union of KP and KQ. Let's go to question 6. And I believe this is the last question of the day. And this is a challenging question. Let G be a bipartite graph of order P plus Q and size PQ, with the minimum degree of G is at least 1. Show that G is KPQ if and only if every 2 edges in G are contained in common C4. We try to understand this question again. If G is a bipartite graph of order P plus Q and the sign PQ, it doesn't mean that G has to be equal to KPQ. Let me give you an example. So let's say P is equals to 3 and Q equals to 5. So PQ is equals to 15. The order is equals to 8 and the size is equals to 15. There are more than one bipartite graph with this condition. That is, number 1, K35, or G is K44 with one edge removed. So in this case, there is a term if and only if. So we will prove one way first. If G is complete bipartite graph, then clearly the result means that every 2 edges in G are contained in a common C4. Okay, now next, if every 2 edges in G are contained in common C4, here we claim that G is KPQ. Again, we'll prove by contradiction. Suppose not. If not true, then axis U and V such that UV are not adjacent. And because the minimum degree of G is 1, U is not adjacent to V, but U must adjacent to some Y in Y, and likewise V must adjacent to some X in X. So meaning that there exists X in X and Y in Y such that UY and XV adjacent. Now we use this assumption now. XV and UY are 2 edges in G, so there must be a common C4. Since it must be a common C4, it will be a contradiction if U is not adjacent to V. Then it is a contradiction if UV not adjacent. Now, in this case, we just shown that if U in X and V in Y and they are not adjacent, something wrong. So meaning that every u in x and every v in y, they has to be adjacent. So it means that G is complete bipartite graph. However, we haven't proved that this complete bipartite graph is KPQ, because it may be of some other form, K, P minus 1, Q plus 1, and so on and so forth. So we will let the number of x is equal to K, and therefore the number of y will be equal to P plus Q minus K, because the order is equal to P plus Q. And therefore, the number of edges in G is equal to K times P plus Q minus K. And it is given that this is PQ. So what we have right now is PQ minus KP plus Q plus K squared equals to 0. After we factorize it, this is P minus K, Q minus K equals to 0. It means that either K equals to P or K equals to Q. For either case, it will mean that G equals to KPQ. And we are done. So that's all for today's lesson. So we have learned some idea in bipartite graph, and we have gone through some of the exercises. So hope you enjoyed it. I'll see you next time. Bye bye.